This is your weekly dose of 3-Eye Atlas, featuring the rotational heartbeat of an interstellar traveler, brought to you by the Sleepy Science 100 channel. Tonight, we drift into the quiet cosmos, following a visitor from beyond our solar system, listening closely to a rhythm written in light and shadow. Now, let us settle in. We will glide through the precise 16.16-hour rotational period, driving gentle pulses of brightness, the comet's nucleus revealing its heartbeat through periodic light curve variations, a slow spin, phased outgassing, a cosmic rhythm breathing through the coma. And so we begin, floating outward through the darkness, toward a body that may have traveled for millions of years, carrying with it a rhythm, an ancient heartbeat, measured now in the patient turning of its nucleus. 16.16 hours, one complete rotation, one full revealing of hidden faces, one cycle of light and shadow and whispered sublimation. Imagine, if you will, the photometric observations cascading in from telescopes scattered across our world, each one catching fragments of brightness, fragments of dimming, as this distant nucleus turns, ever so slowly, in the vast emptiness between stars. The data points gather like soft snow, accumulating into patterns, into curves, into the unmistakable signature of periodic variation, a clear rhythm emerging from the noise, a pulse rising and falling with the patience of geological time compressed into hours. As we drift together through this gentle cosmic cadence, if you find these quiet journeys through sleep and space calming or meaningful, you're warmly invited to subscribe. Liking the video helps us know these explorations are reaching you. And if you're still awake, before you fully drift off, feel free to leave a single word in the comments describing how you hope to feel in the morning. Rested, calm, clear. Thank you for joining us tonight as we drift far, far out, listening to the soft, steady pulse of 3 Atlas. The dominant period reveals itself. 16.16 hours, not a random number, but the echo of the nucleus itself, spinning, turning its faces toward us, then away, then toward us again. This rotation, this slow cosmic waltz, drives everything we see, every brightening, every dimming, every subtle shift in the light that reaches us across millions upon millions of kilometers. It is, in essence, the heartbeat of an ancient body, a pulse that has beat steadily, unchanging, through the darkness between the stars. When we examine the light curve, the graph of brightness over time, we find an amplitude, a measure of how much the brightness changes, reaching approximately 0.3 to 0.5 magnitudes. This may seem like a small variation, a gentle fluctuation, but it tells us something profound. The nucleus is not spherical, not a perfect ball of ice and rock, but elongated, perhaps stretched, like a cosmic egg, or possibly bilobate. 2 lobes join together, turning end over end in the void. Each time the long axis points toward us, we see more reflective surface, more brightness, and as it rotates away, presenting its narrower profile, The light dims, a gentle exhalation, before the next inhalation of illumination. Some datasets reveal a double-peaked structure, 2 maxima, 2 minima, within each 16.16-hour cycle, suggesting we are seeing both ends of an elongated shape, while other observations show single-peaked components, perhaps when viewing angles change, or when outgassing from active regions overwhelms the geometric signal. The pulse adapts, shifts, reveals different facets of its nature, while maintaining its underlying 16-hour cadence, its patient, unwavering rhythm. The astronomers who discovered this period, who teased it from the scattered observations, used elegant mathematical techniques, phase dispersion minimization, a method that tests countless possible periods, seeking the one that brings order to apparent chaos, that aligns all the brightness measurements, folding them into a coherent pattern. The Lomskargel periodogram, another tool, confirmed what the first method suggested. 16.16 hours, a signal strong and clear, rising above the noise like a beacon, a cosmic metronome, counting out the seconds, the minutes, the hours of this interstellar visitor's patient rotation. These observations span months, from July through December 2025, as 3 Atlas swept through the inner solar system, approaching, brightening, then receding, fading back into the cosmic depths. Multiple telescopes contributed, each adding pieces to the puzzle, creating dense phase coverage, ensuring that no part of the rotation remained hidden. Gemini north and south, powerful instruments perched on volcanic mountains, provided high-precision photometry, measurements of exquisite accuracy, while amateur networks, comets, the British Astronomical Association, supplied long-term monitoring, patient vigils, night after night, capturing the steady pulse, the unwavering rhythm of this distant nucleus. And here is where the story deepens, where rotation becomes more than just spin. The brightness pulses. These regular fluctuations correlate with changes in the coma morphology, the shape and structure of the dust and gas clouds surrounding the nucleus. As the nucleus turns, as specific regions rotate into sunlight, outgassing jets modulate in intensity, brightening when active regions face Earth, dimming when they turn away. The rotational whisper shapes visible jets, creates patterns, structures that appear, strengthen, and fade, all in synchrony with that 16.16-hour heartbeat. We can see this phased awakening, these jets appearing brighter when their source regions face us directly, their brightness tied intimately to the rotational phase, to the exact orientation of the spinning nucleus. The entire coma brightness, the overall glow of gas and dust, shows rotational modulation, pulsing gently in time with the nucleus, a cosmic breathing, an exhalation of volatiles, timed to the ancient spin, the primordial cadence that has persisted across unimaginable distances. From these observations, from the asymmetry of the light curve, scientists infer the orientation of the nucleus spin axis, the invisible pole around which everything rotates. The obliquity, the tilt of this axis, is likely high, creating seasonal outgassing patterns, ensuring that different latitudes receive varying amounts of sunlight over the course of each rotation, driving complex patterns of sublimation, of jets, of dust release, all governed by that slow, patient 16.16-hour rhythm. Now, consider this. 16.16 hours is unusual, surprisingly slow, for a small cometary nucleus. Typical solar system comets, bodies born in our own stellar neighborhood, spin faster, much faster, with periods of 5 to 10 hours, quick rotations, rapid cycles. But for Atlas, this interstellar traveler, takes its time. 16.16 hours places it among the slower rotators, bodies that turn with deliberate patience, preserving something from their formation, some quality of their birth. This slow spin may preserve primordial angular momentum, the original rotation rate from when this body first coalesced, perhaps in a circumstellar disk orbiting a young star light years from here. Billions of years ago, interstellar travel, the long journey through the void, may dampen rotational excitation. There are no collisions in the interstellar medium to spin it up, no gravitational encounters to transfer energy, just the slow, steady, unchanging rotation, conserved across the parsecs, across the eons, a heartbeat echoing billions of years, and remarkably, no significant period change has been detected over the months of observation. The upper limit on period variation is less than 0.01 hours, essentially unmeasurable. This rules out rapid spin-up from outgassing torques, the forces that jets might exert on the nucleus, trying to change its rotation. Yet 3i Atlas resists, maintains its rhythm, suggesting the nucleus is likely monolithic, a single coherent body, or at most loosely bound, but structurally stable. Not a contact binary tumbling chaotically, not a rubble pile threatening to fly apart. The light curve shape remains stable, month after month, rotation after rotation, suggesting structural integrity, a body that holds together, that maintains its form, despite the stresses of outgassing, despite the thermal cycling, despite everything the solar environment throws at it. The amplitude stays consistent across different filters. Red light, visual wavelengths showing similar modulation, and near-infrared observations confirm that this is a nucleus-dominated signal, that we are truly seeing the body itself, not just coma brightness variations. Careful analysis subtracts the coma contribution using profile-fitting, mathematical models that separate the diffuse cloud from the solid nucleus, revealing the pure rotational signal beneath. And when we align this signal with jet visibility cycles, we find perfect correlation. Specific jets brighten at predictable phases, appearing like clockwork as their source regions rotate into view. Phase-folded images, where many rotations are stacked together, reveal repeating structures, patterns that emerge, sharpen, then fade, only to emerge again 16 hours later, a cosmic rhythm, a dance of illumination. The Nordic Optical Telescope captured time series observations, watching full cycles unfold, documenting the complete rotation from peak brightness through dimming to minimum, then back to peak, a complete circuit, a full revelation of this ancient body's shape and activity. And at closest approach, when 3C Atlas swept nearest to Earth, Keck Observatory's adaptive optics, technology that corrects for atmospheric turbulence, resolved the nucleus, actually separated it visually from the surrounding coma, providing direct constraint on its size. From absolute magnitude measurements, from the total amount of light reflected, astronomers estimate the nucleus diameter at 4 to 8 kilometers, assuming a low albedo, a dark surface, around 0.04 to 0.06, similar to charcoal, to coal. These rotational light curves, these brightness variations, feed into shape models, mathematical reconstructions of the three-dimensional form. Ellipsoid models fit the data well, with axis ratios of 1.5 to 2.1, one dimension half again or twice as long as another, an elongated form, turning slowly, showing us first its broadside, then its narrow edge, then broadside again, in endless patient cycles. Such a shape, at such a slow rotation, would not maintain hydrostatic equilibrium, would not be held in a relaxed spherical form by its own gravity. Instead, strength must come from primordial ices, or perhaps even metals, internal cohesion, material bonds that resist deformation, that keep this ancient structure intact. The outgassing torque, the push of jets trying to change the rotation, proves insufficient to alter the period significantly. The body resists, maintains its ancient rhythm, its primordial pulse, the non-gravitational acceleration, the tiny push that outgassing exerts on the comet's orbit shows no rotational signature, no 16.16-hour variation, suggesting the net force averages out over each rotation, that active regions are distributed, balanced, not concentrated on one hemisphere. This pulse rhythm, this 16-hour heartbeat, becomes visible in the overall brightness evolution, in how the comet brightened as it approached the sun and dimmed as it receded, pre-perihelion, before closest approach to the sun. The light curve was weaker, but still present, a subtle pulse, a gentle variation. Then post-perihelion, after that closest passage, the amplitude increased with activity, as outgassing strengthened, as more volatiles sublimated away. This seasonal enhancement, active areas becoming illuminated, drove stronger modulation, deeper brightness variations, while maintaining that same 16.16-hour cycle, that unchanging heartbeat. The diurnal cycle, the day-night rhythm on the nucleus surface, drives volatile sublimation patterns. CO2 and CO, carbon dioxide and carbon monoxide, sublime, turn from ice directly to gas, modulated by insolation, by how much sunlight strikes each region. Water ice activation occurs deeper, less directly influenced by the rotation, requiring more sustained heating. But the supervolatiles, the ices that evaporate easily, respond immediately to the rotational cycle, to the 16-hour dance of illumination, jet collimation. The remarkable narrowness of these outgassing streams is maintained across rotations. The slow spin, 16 point on 16 hours of patient turning, prevents smearing of narrow jets, allows persistent jet structures, features that last for hours, that remain coherent, that don't blur into a general haze. This slow rotation permits the jets to maintain their identity, their directionality, their focused streams of gas and dust, all phased to the nucleus heartbeat, stacking multiple rotation cycles, combining observations from many 16.16-hour periods, enhances faint jet visibility, brings out structures too subtle to see in single rotations. November 2025 campaigns, when professional astronomers and citizen scientists coordinated observations, covered multiple complete cycles, each rotation adding data, adding confidence, refining the period measurement. This professional amateur collaboration, this union of large telescopes and backyard instruments, refined the period to exquisite precision, ruled out period aliasing, eliminated false signals that might arise from incomplete sampling. A harmonic at 8.08 hours, exactly half the true period, was rejected as the primary signal. The full 16 or 16-hour cycle, with its double peak structure, better explained all the observations, accounted for all the brightness variations. The distinction between sidereal and synodic periods, between rotation relative to the stars versus relative to the sun, was carefully considered, and corrections for Earth's motion, our own planet's orbital movement, were applied to the analysis, ensuring the measured period truly reflected the nucleus rotation, not artifacts of our changing viewpoint. This nucleus pulse influences even the coma density waves, enhancements in gas and dust density that propagate outward, spreading rhythmically into space, carried by the solar wind and radiation pressure, each pulse of outgassing, each rotation bringing active regions into sunlight, sends another wave, another enhancement, rippling through the coma, moving outward at hundreds of meters per second, creating subtle structure, patterns that extend far beyond the nucleus, echoes of that central 16-16-hour heartbeat, rhythmic pulses moving outward forever into the cosmic night. Even the anti-tail and tail features, those delicate structures of dust and gas, show slight modulation with the rotation, subtle variations in brightness and morphology, tied to which hemisphere faces sunward, which active regions pour their contents into space at any given moment. The color variations are subtle, requiring careful measurement, but they exist. Green emission from diatomic carbon, from C2 molecules excited by sunlight, appears stronger from the more active hemispheres, from regions where outgassing is most vigorous, where fresh material sublimates into the vacuum. Dust release becomes episodic, tied to rotational facing, when an active region rotates into direct sunlight, into the most intense heating, dust production surges. Particles are lifted from the surface, carried away by expanding gases. Then, as that region rotates into shadow, into the long night of the nucleus, production wanes, drops, until the next rotation brings dawn once more. This slow rotation, this 16.16-hour patient cadence, preserves jet coherence over days. A jet born when a region faces the sun can remain visible, relatively unchanged, for hours, even as the nucleus continues its slow turn, its eternal waltz. We might compare 3I Atlas to 67P Churyumov-Gerasimenko, that celebrated comet visited by the Rosetta spacecraft, which has a rotation period of 12.4 hours, faster than our interstellar visitor, yet similar in many ways. 67P showed strong rotational modulation, clear brightness variations, phased out gassing that created predictable patterns, jets that appeared and disappeared with clockwork regularity. And here we find 3I Atlas, born light years away, in some distant stellar system, showing remarkably similar behavior, phased out gassing, rotational control of activity. The interstellar origin doesn't prevent familiar rotational behavior, doesn't create something entirely alien. Instead, we see, perhaps, universal principles, physics that operates the same way, whether a comet formed around our sun or around some other star, now lost to identification. This spin state, this 16-16-hour rotation, likely reflects the formation environment in that distant system, perhaps a gentle accretion process, particles slowly gathering, building up, without violent collisions that would spin the growing body faster, or perhaps formation in a region of the protoplanetary disk where material moved slowly, where angular momentum was low excitation from gentle ejection, from being lifted out of its birth system not by violent encounter, but by some subtler process, gravitational perturbation perhaps, or slow migration to the edge of planetary influence, then release into the galaxy, and once in interstellar space, there are no collisions to spin it up. The interstellar medium is almost perfectly empty, a few atoms per cubic centimeter, nothing that could impact with enough mass, enough energy, to change the rotation of even a small nucleus. So the primordial rotation, the original spin from formation, is conserved, preserved, across millions or billions of years, across parsecs of empty space. This pulse rhythm truly becomes the heartbeat of an ancient body, beating steadily, unchanged, since before our solar system might have even existed. All this data, these thousands of photometric measurements, flow into light curve databases, digital archives that preserve the phase data, making it available for future analysis, for comparison with other objects, for refinement as new techniques emerge, and there will be future observations, as long as 3I Atlas remains bright enough, tracking its long-term stability, watching for any changes, any evolution in the rotational period. Any period change would indicate mass loss asymmetry, that outgassing is removing material unevenly, creating torques, forces that alter the spin. But so far, the upper limit on such changes constrains outgassing distribution, suggests remarkable balance, symmetry in how this nucleus releases its volatiles. Through rotational synthesis, combining observations from many different viewing angles, many different rotation phases, astronomers can attempt nucleus mapping, creating maps of the surface, identifying where active regions lie, where inert terrain dominates. Estimates suggest active area fractions of 10 to 30%, meaning only a modest portion of the surface actually produces jets, actually sublimates significantly. The rest remains dormant, covered perhaps in non-volatile lag deposits, dust and organics left behind as ices sublimate, building up over time, insulating the ice beneath. From the light curve, from the way brightness changes with rotation, from the amplitude and shape, scientists can infer the inertia tensor, a mathematical description of how mass is distributed, how the body resists changes to its rotation. This connects to structural questions, to whether the nucleus is homogeneous, uniform throughout, or differentiated, with denser material in some regions. But the stable rotation, the unchanging period, the coherent light curve, all suggest internal homogeneity, a body mixed relatively uniformly, without large-scale internal structure that would complicate the spin dynamics. Slow rotators like 3I Atlas are indeed more common among larger nuclei, among bodies with diameters of several kilometers or more. There's a size-rotation relation. Smaller bodies tend to spin faster, perhaps because they're more easily spun up by outgassing torques, or because they're fragments from collisions that imparted high angular momentum. The fact that 3I Atlas, with its estimated 4 to 8 kilometer diameter, fits this trend, extends the size-rotation relation to interstellar objects, suggests that the same physical principles, the same evolutionary pathways operate across stellar systems. For low-density bodies, porous structures with bulk densities below 500 kilograms per cubic meter, slow rotation makes sense. Less dense than water, more like a sponge than a solid rock. Such bodies have weak internal strength, can't withstand the centrifugal forces of rapid rotation. They would fly apart, disintegrate, if spun too quickly. So, slow rotation, 16.16 hours of patient turning, allows structural stability, permits a porous structure from pristine accretion, from gentle accumulation of icy particles that never compressed fully, never sintered into solid ice, retaining voids, spaces, weakness. This rotational pulse, this heartbeat, reveals that internal homogeneity through its regularity, through its stability. If there were subnuclei, smaller bodies orbiting within the coma, or satellites, companions to the main nucleus, they would complicate the light curve, add additional periodicities, create irregularities, but none are detected. The pulse is clean, pure, a single dominant frequency. 16.16 hours, nothing more. This stable spin excludes recent disruption, rules out a recent breakup, a splitting event that would leave the fragments tumbling chaotically, spinning irregularly. Instead, we see ancient stability, primordial calm. The pulse itself becomes a diagnostic of structural strength. How well does this body hold together? How strong are the internal bonds? The fact that it maintains coherent rotation, that it doesn't wobble, doesn't precess rapidly, suggests adequate strength, sufficient cohesion to maintain its form. This data informs models of extrasolar nucleus evolution, helps us understand how cometary bodies form, evolve, survive in planetary systems beyond our own. Each measurement, each rotation cycle captured, adds to our understanding not just of 3i Atlas, but of comets in general, of icy bodies throughout the universe. As the comet recedes, as it moves farther from the sun, farther from Earth, the rhythmic signal grows fainter, dimmer, harder to detect. The final cycles are captured in late 2025, pushing telescopes to their limits, extracting signal from noise, before the comet becomes too faint for photometry, too dim to measure accurately. But those last rotations, those final pulses, are preserved, archived, added to the complete record of this interstellar visitor's passage through our realm. Let us drift deeper now, into the subtleties, into the quiet nuances of what this 16-hour heartbeat reveals. Consider how light itself becomes our messenger, photons reflected from the nucleus surface, traveling millions of kilometers, carrying information about brightness, about color, about the orientation and activity of a body too small, too distant to resolve clearly even with our finest telescopes. We reconstruct, we infer, we deduce from these scattered messengers the nature of their source. The phase dispersion minimization technique, this mathematical tool, essentially asks a simple question over and over. If I assume the period is X hours, and I fold all my observations according to that period, arranging them as if they came from repeated cycles of X hours, do they line up coherently, or do they scatter randomly? The true period, 16.16 hours, creates order, creates a clear pattern, while wrong periods leave only chaos, only scattered points with no relationship. It's elegant, beautiful. How mathematics can extract signal from what appears to be noise, finding the hidden rhythm, the concealed heartbeat, and the Lomskargel periodogram. This complementary approach builds a power spectrum, showing which frequencies, which periods are present in the data. Strong signals, true periodicities, appear as peaks, as spikes in the spectrum, rising above the baseline, and at 16 hours, there it stands, clear and unmistakable, a peak that dominates, that announces itself as the fundamental frequency, the primary rhythm driving all the brightness variations we observe. Through July, August, September, observers around the world, on different continents, under different skies, contributed their measurements, some from high mountain observatories where thin air creates steadier seeing, sharper images, others from amateur setups in backyard gardens, modest telescopes guided with passion and patience. Together they wove a nearly continuous monitoring campaign, patching the comet at different rotation phases, ensuring complete coverage, filling gaps, creating redundancy, each observer adding threads to the tapestry, building toward complete understanding. The Gemini telescopes, twins separated by hemisphere, one on Mauna Kea in Hawaii, one on Cherapachon in Chile, provided complementary coverage. When the comet set below the horizon for one, it rose for the other. This global perspective, this planetary coordination, allowed tracking the rotational heartbeat continuously, catching every pulse, missing no beat. The precision of these instruments, their sophisticated detectors, their adaptive optics and careful calibration pushed uncertainties down, refined measurements, revealed subtle details that smaller instruments might miss. Yet the amateur networks proved equally vital. Comets, the Comet Observation Network, coordinated by dedicated amateur scientists, provided long-term baseline, night-after-night observations that professionals conducting targeted campaigns might not achieve. The British Astronomical Association, with its comet section and disciplined observers, added their careful photometry, their patient measurements. This marriage of professional precision and amateur dedication created something neither could achieve alone: a complete picture, a full understanding of 3-eye Atlas's rotational behavior. Now observe how brightness pulses correlate with coma morphology changes. It's not just that the nucleus itself brightens and dims, but the entire cloud of dust and gas, the coma that surrounds and obscures the nucleus, responds to the rotational cycle. As active regions rotate into sunlight, they erupt more vigorously, pouring more gas and dust into the coma, creating localized brightenings, enhancements that move outward, expand, evolve. All phased to that 16.16-hour heartbeat, all synchronized to the slow turn of the ancient nucleus. Outgassing jets, these collimated streams modulate in intensity with rotation phase. We can measure this, photograph it. See jets brighten as their source regions face Earth, as our line of sight looks directly down into the active area, seeing maximum brightness, maximum contrast. Then as rotation carries that region to the limb, to the edge of the visible disk, and eventually around to the far side, the jet dims, fades, disappears from view, only to reappear 16.16 hours later, when rotation brings it back, brings it around for another showing, another display of activity. These phased jets appear brighter when active regions face Earth, but they exist always, constantly. They continue to emit on the far side, invisible to us but real, genuine. It's only our perspective that changes. only our ability to see that varies with phase. This reminds us of the limitations of observation, that we see only one face at a time, only one hemisphere, and must infer the whole from the parts, must reconstruct the complete reality from fragmentary glimpses. The entire coma brightness shows rotational modulation, a gentle pulsing, expanding and contracting in luminosity, breathing with the nucleus heartbeat. This isn't just the nucleus light varying, but the total system, nucleus plus coma, responding as one to the rotational cycle. The slow rotation allows us to separate these effects, to distinguish nucleus contribution from coma contribution. If the rotation were much faster, several hours or less, these effects might blur, might become indistinguishable. But at 16 hours, there's time, patience, space to observe and analyze each component distinctly. From light curve asymmetry, from the fact that the two peaks in each cycle aren't quite identical, that one maximum is slightly brighter than the other. Astronomers infer the spin axis orientation. They build models, computer simulations, that predict what we should see for different axis tilts, different obliquities, and compare these predictions to observations. The best match, the model that most closely reproduces what we actually see, likely reflects reality, gives us the true orientation, invisible but deduced, unknown but knowable through patient analysis. High obliquity means the spin axis points far from perpendicular to the orbital plane, creates seasons, long periods where one polar region receives sustained illumination while the other languishes in darkness, then reversal, switching, as the comet moves along its trajectory. This drives seasonal outgassing patterns, variations that play out over weeks or months, distinct from but complementary to the rapid 16.16-hour rotational variations. Multiple timescales, multiple rhythms, all interacting, all contributing to the complex behavior we observe. That three-eye atlas spins slowly, taking 16.16 hours per rotation, places it in rare company among small comets. Most nuclei we've studied thoroughly, through spacecraft visits or detailed Earth-based campaigns, rotate faster. 5 to 10 hours is typical. Some spin even faster still, just a few hours per rotation, rotating rapidly enough that material near the equator feels significant centrifugal force, reducing the effective gravity, making it easier for dust and chunks to lift off, to escape into space. But 3i Atlas resists this trend, maintains its slow pace, its patient rhythm. Why this difference? Several possibilities emerge. Perhaps interstellar comets form differently, accrete more gently, without the violent impacts that might spin up solar system comets during the chaotic planet formation era. Or perhaps slow rotators exist in both populations, but we've simply not observed enough interstellar objects yet to know their true distribution. With only a handful of confirmed interstellar visitors, 2 comets, 1 asteroid-like object, statistics remain uncertain. Each new measurement, each new interstellar object discovered and characterized, refines our understanding, narrows the possibilities. This slow spin might genuinely preserve primordial angular momentum, the rotation rate from birth, from initial formation. Imagine the earliest moments, dust and ice grains in a protoplanetary disk, colliding, sticking, gradually building larger aggregates. Each collision transfers momentum, angular momentum, spin. But if those collisions are gentle, low velocity, the net spin accumulates slowly. The final rotation period depends on countless small impacts, their speeds, their angles, their randomness, for a body forming in a quiet disk region, where turbulence is low, where collisions are soft. Slow rotation emerges naturally, inevitably. Then ejection into interstellar space. However it occurred, whether gravitational scattering by a giant planet or slow migration through disk resonances or passage near the forming star itself, the process releases this body into the galaxy, and in interstellar space, conditions preserve that primordial rotation. There's nothing to change it. The interstellar medium contains approximately 1 atom per cubic centimeter in dense regions, far less in typical regions. Such low density means effectively no collisions, no impacts, nothing to transfer angular momentum. The radiation pressure from starlight is too weak, too diffuse, to significantly affect rotation. So the nucleus spins on, unchanged, unaltered, conserving its angular momentum across light years, across eons, billions of years perhaps. This body might have formed when the universe was younger, when the galaxy had different structure, when our own solar system didn't yet exist. And all that time, all those billions of rotations, perhaps 500 billion complete turns if it's truly several billion years old, the period remained constant, 16.16 hours, 16.16 hours, 16.16 hours, an ancient metronome, a cosmic clock, keeping time through the darkness, through the lonely voyage between stars, that no significant period change appears over months of observation, that the upper limit is less than 0.01 hours, less than 36 seconds of variation, tells us the outgassing torques are remarkably balanced. Any asymmetry in volatile distribution, any concentration of active areas on one hemisphere, would create net torque, would try to spin the nucleus up or down, alter its rotation. But we see none of this, suggesting either that active areas are symmetrically distributed, balanced across the surface, or that torques from different regions cancel, oppose each other, some to nearly zero. This rapid spin-up, acceleration of rotation, occurs on some active comets. We've observed it, measured it, seen rotation periods decrease by minutes or even hours over a single apparition as outgassing torques act cumulatively, spinning the nucleus faster. But 3i Atlas shows no such behavior, remains stable, constant. This suggests either low activity levels, modest outgassing that creates weak torques, or again, that balanced distribution, geometric arrangement that prevents net acceleration. For the nucleus to resist these torques, to maintain period stability, it must be coherent. A rubble pile, a collection of loosely bound fragments, might change rotation more easily, might respond to even weak torques. But a monolithic nucleus, or one that's loosely bound but still structurally integrated, resists, maintains its spin state despite the forces acting upon it. The light curve stability supports this. No tumbling, no complex rotation, no nutational wobbles, just clean, regular, periodic variation. A double-peaked curve that repeats precisely, rotation after rotation. No evidence of contact binary tumbling. Two bodies in contact, touching but distinct, often show complex light curves, multiple periods, irregular variations as they wobble, as gravitational and structural interactions create complicated dynamics. But 3i Atlas shows none of this complexity, suggesting either a single monolithic body, or if bilobate, two lobes so firmly connected that they rotate as one, move as one, present as one coherent object. The light curve shape holds stable across filters, red wavelengths, visible wavelengths, even extending into the near-infrared. All show the same modulation, the same amplitude, the same period. This wavelength independence confirms the geometric origin, that we're seeing shape, rotation of an elongated body, rather than compositional variations, surface patches of different color or reflectivity rotating into view. If the latter dominated, we might see different periods in different wavelengths, but we don't. We see consistency, uniformity, geometric control. Near-infrared observations prove especially valuable. At these longer wavelengths, dust scattering is less efficient. Coma contribution decreases, allowing the nuclear signal to dominate, to emerge more clearly, confirming that the observed modulation truly comes from the nucleus, from the solid body, not from brightness variations in the surrounding cloud. This nucleus-dominated signal gives confidence, ensures that the 16.16-hour period truly reflects nuclear rotation, the physical spin of the solid object at the heart of the coma. Careful analysis must subtract coma contribution, profile fitting, examining how brightness varies with distance from the nucleus, allows separation. The nucleus light is concentrated, central, while coma light is distributed, extended, falling off with distance according to predictable patterns. By modeling this distribution, by fitting functions to the observed profiles, astronomers can remove the coma contribution, isolate the nucleus, see its true brightness, its pure rotational modulation. And when this clean signal is aligned with jet visibility cycles, the correspondence is striking. Specific jets brighten at predictable phases. Observers learn to anticipate. In 2 hours we should see the northern jet strengthen. At phase 0.6, the spiral feature emerges. This predictability, this clockwork behavior, demonstrates the intimate connection between nucleus rotation and observed activity. They are not independent, not separate, but linked, bound together by geometry and physics into one coherent system. Face-folded images reveal repeating structures with beautiful clarity. Individual images, single frames, show jets, features, details, but with noise, with uncertainty. But when many rotations are combined, aligned by rotational phase and stacked, those real features strengthen, sharpen, while random noise averages away, fades to insignificance. What emerges are the true persistent structures, jets that repeat rotation after rotation, boundaries between active and inactive regions, patterns that are genuine, reliable, reproducible. The Nordic Optical Telescope time series captured complete cycles. This observatory, on La Palma in the Canary Islands, pointed at 3-eye Atlas for hours at a stretch, taking image after image, creating sequences, movies essentially, of the brightness evolution, watching the curve rise, peak, fall, trough, rise again. One complete 16.16-hour cycle documented in detail, then another, building the data set that would confirm the period, constrain the amplitude, reveal the shape of this ancient heartbeat. At closest approach, when 3-eye Atlas passed nearest Earth, Keck Observatory activated its adaptive optics system. This remarkable technology, using deformable mirrors that change shape hundreds of times per second, corrects for atmospheric turbulence, sharpens images to near theoretical perfection. And through this system, the nucleus was resolved, separated visually from the coma, appearing as a distinct point source, a stellar image, amid the surrounding glow. This resolution allowed direct size estimation, direct measurement uncomplicated by coma contamination, yielding that 4 to 8 kilometer diameter estimate. These numbers assume a low albedo, dark surface reflectivity, around 0.04 to 0.06, meaning only 4 to 6% of incident sunlight reflects back, the rest absorbed. The assumption comes from measurements of other cometary nuclei, from spacecraft visits showing surfaces dark as asphalt, as charcoal, covered in complex organic molecules, radiation-processed materials that absorb light efficiently, convert it to heat. These dark surfaces are the norm for comets, for bodies that have traveled through space for billions of years, exposed to cosmic rays, to ultraviolet radiation, to the slow chemical transformations that darken and redden primitive materials. From the rotational light curves, from their precise shape and amplitude, scientists construct mathematical models of the three-dimensional form. These ellipsoid models, simple geometric shapes, prolate spheroids stretched along one axis, fit the observations remarkably well. Axis ratios of 1.5 to 2.1 emerge from the fitting, meaning if one dimension measures 8 kilometers, another measures perhaps 4 or 5 kilometers. This elongation, this departure from spherical symmetry, creates the brightness variations we observe. More surface area presented when the long axis points toward us, less when we see the narrow profile. But such a shape, rotating at 16.16 hours, would not naturally form from hydrostatic equilibrium. A fluid body, or one soft enough to flow over time, would relax into a sphere or a oblate spheroid, flattened at the poles by centrifugal force. The fact that 3i Atlas maintains elongation, maintains shape that deviates from equilibrium, tells us about strength, about internal structure. The nucleus must possess cohesive strength, must be held together by forces beyond mere gravity, perhaps primordial ices, water ice strong enough to resist deformation at the cold temperatures of interstellar space, or perhaps organic cements, complex molecules binding grains together, or even metals, though less likely in a comet, iron or silicate frameworks providing structural rigidity. The outgassing torque, the mechanical push that jets exert as they erupt from the surface, proves insufficient to alter the period significantly. We can calculate expected torques, estimate the forces based on observed outgassing rates, and compare them to the moment of inertia, the rotational resistance of the nucleus. And we find that expected changes over months of observation should be detectable, should show up as period variations. Yet they don't appear. This tells us either that torques are weaker than estimated, that our understanding of the outgassing is incomplete, or more likely that they're balanced, that jets on opposite hemispheres or at different locations create opposing torques that cancel. Maintaining rotational equilibrium, the non-gravitational acceleration. This is the orbital perturbation caused by outgassing. When gas erupts from the nucleus surface, it carries momentum and, by Newton's third law, pushes back on the nucleus, changing its velocity slightly, altering its orbit minutely. For most comets, this is measurable, affects the predicted position, must be accounted for in trajectory calculations. And for 3i Atlas, this acceleration exists, has been measured, but critically, it shows no rotational signature, no 16-to-16-hour variation, no modulation in phase with the nucleus spin. This absence of rotational signature in the non-gravitational force suggests that the net thrust averages to approximately the same value over each rotation, even though individual jets strengthen and weaken with phase, even though outgassing varies dramatically across the surface. The total momentum transfer, the vector sum of all jets, remains relatively constant. This implies distributed activity, multiple source regions spread across the nucleus, not concentrated on a single active hemisphere that would create strong rotational modulation in the thrust. Yet we do see the pulse rhythm in overall brightness evolution. We can watch the comet as a whole brighten, approaching the sun, increasing in total luminosity, and within that general trend, that smooth curve, we can detect the 16.16-hour variations, the heartbeat persisting, continuing, never ceasing, from the outer solar system, when the comet was still faint, still distant, through perihelion passage, the closest approach when activity peaked, and then outward again, receding, cooling. The pulse continued, a faithful companion, a steady rhythm underlying all the changes. Pre-perihelion observations, those conducted before closest solar approach, showed weaker light curve amplitude. The comet was less active then, cooler, fewer volatiles sublimating, jets weaker, more subtle. Yet even then, careful photometry revealed the 16.16-hour period, detected the modulation, saw the pulse. This demonstrated the robustness of the signal, proved it wasn't merely an artifact of high activity, but a fundamental property of the nucleus, visible at all activity levels, from distant quiescence to perihelion vigor. Post-perihelion, after that close passage, after the sun's intense radiation had heated the nucleus, driven off layers of material, enhanced sublimation rates, the light curve amplitude increased, the same 16.16-hour period, but larger variations, stronger pulses, deeper troughs and higher peaks. This amplitude increase reflected higher activity, more vigorous outgassing, creating stronger contrast between active and inactive regions, between areas facing the sun and those in shadow. The seasonal enhancement, this strengthening of rotational modulation, came as active areas became more productively illuminated, as thermal waves penetrated deeper, as subsurface ices began participating in sublimation. Now consider the diurnal cycle on the nucleus surface, day and night, not measured in 24 hours like Earth, but in 16.16 hours, that being the local day on 3 Atlas. Imagine standing on that surface, watching the sun rise, slowly, taking hours to climb from horizon to zenith. The temperature rises. The ice beneath your feet begins to sublime. Gas erupts, dust lifts, jets form, peak brightness, peak activity, then sunset, gradual cooling, the gas production wanes, jets fade, darkness falls, temperatures plummet, and all grows quiet until 16 hours later, dawn returns and the cycle begins anew. This diurnal cycle drives volatile sublimation patterns in wave-like fashion. The supervolatiles, CO2 and CO, carbon dioxide and carbon monoxide, respond quickly to temperature changes. They sublime at low temperatures, react immediately to sunrise, create the early morning jets, the dawn activity, water ice, the dominant volatile in most comets, requires higher temperatures, needs more sustained heating. It activates later in the local day, perhaps hours after sunrise, when the surface has absorbed enough solar energy to heat the subsurface, to reach the depths where water ice resides. So the sublimation pattern evolves through each 16.16-hour rotation. First come the CO2 and CO jets, sharp, responsive, tied closely to the rotation phase. Then water sublimation builds, more gradual, less sharply phased, creating a more sustained background, and dust release, depending on gas production to drag it aloft, follows the volatile pattern, episodic with the supervolatiles, more sustained with water. All of this choreographed by rotation, by the 16.16-hour heartbeat, by the ancient rhythm that governs every process on this interstellar visitor. The jet collimation, the remarkable narrowness of these streams, depends critically on slow rotation. If the nucleus spun rapidly, say every 2 or 3 hours, jets would sweep across the sky quickly, would smear, would blur into broader fans, losing their sharp definition. But at 16 hours, each jet remains nearly stationary relative to the stars, maintains its orientation for hours, allows the gas and dust to stream outward in a coherent beam, a focused thread, a structure that persists, that remains identifiable rotation after rotation. This slow rotation preserves jet coherence, allows persistent structures that we can track, study, analyze over extended periods. Phased stacking enhances faint jet visibility through a beautiful statistical process. Imagine you have 20 images, each showing a jet barely above the noise. Difficult to see, uncertain. But if all 20 images are taken at the same rotational phase, when the jet points in the same direction, you can align them, stack them, add their signals together. The real jet, present in the same location in all images, reinforces, strengthens, grows to 20 times its single image brightness, while random noise, different in each image, averages toward 0, fades to insignificance. What emerges is structure, features too subtle for single observations, revealed through the power of repetition, through the gift of multiple rotation cycles. The November 2025 observation campaigns exemplified coordinated effort. Professional observatories allocated time specifically for 3i Atlas, Keck, Gemini, the Nordic Optical Telescope, others, all pointing at this visitor, capturing rotation after rotation, and simultaneously, amateur astronomers worldwide, in backyards, on suburban streets, in rural dark sky sites, contributed their observations, their light curves, their carefully calibrated photometry. Together they covered multiple complete 16 hour cycles, ensuring no phase went unobserved, no part of the rotation remained hidden. This professional amateur collaboration refined the period to exquisite precision. Early estimates, based on limited data, suggested periods ranging from 15.5 to 17 hours. But as more data accumulated, as phase coverage improved, the estimate converged, narrowed, settled on 16 hours, with uncertainty of perhaps 0.01 hours or less. This precision arose from combining quantity and quality, many observations spanning months, each individually perhaps uncertain, but collectively definitive, overwhelming, indisputable. Period aliasing, this potential pitfall, had to be carefully eliminated. Aliasing occurs when sampling is irregular, when gaps exist in observations, potentially creating false periods. Harmonics or subharmonics of the true period that might masquerade as the fundamental. To rule this out requires dense sampling, observations that catch the comet at many different rotation phases, that leave no large gaps, no opportunities for false signals to hide. The November campaigns achieved this, and combined with earlier data, confirmed that 16 hours was genuine, real, the actual rotational period. A harmonic at 8.08 hours, exactly half the true period, emerged in some early analyses. This would correspond to a single peaked light curve, one maximum and one minimum per rotation, which might occur if the nucleus was spheroidal with a single bright spot, or had some other simple asymmetry. But closer examination, looking at the detailed light curve shape, revealed the double-peaked structure, 2 maxima per 16.16-hour cycle, definitively establishing that 16.16 hours, not 8.8 hours, represented the complete rotation, the full cycle. The distinction between sidereal and synodic periods matters for precision work. Sidereal period is rotation relative to the fixed stars, the true spin rate of the body itself. Synodic period is rotation relative to the sun. What an observer on the nucleus surface would measure as the day length, including both the rotation and the orbital motion, for objects far from the sun, moving slowly in their orbits. These differ negligibly, but for comets passing through the inner solar system, moving rapidly, the distinction becomes measurable. Astronomers must carefully specify which they're measuring, apply corrections to derive the true sidereal rotation from synodic observations. Similarly, Earth's orbital motion affects observations. Our planet moves, changes position, alters viewing geometry continuously. These effects must be accounted for, light travel time corrections applied, geometric factors considered, all to ensure that the measured 16.16-hour period truly reflects the nucleus rotation, not artifacts of our changing perspective, of our motion through space as we observe. The nucleus pulse influences coma density waves in subtle but detectable ways. When outgassing strengthens during a particular rotation phase, it injects more material into the coma, creates a local density enhancement, a small increase in the number of gas molecules and dust particles per cubic meter. This enhancement doesn't stay put. It propagates outward, carried by the expanding gas, moving at typical velocities of hundreds of meters per second, perhaps 500 to 1,000 meters per second for the gas, slightly slower for dust dragged along. These density waves ripple through the coma like waves on water, spreading, expanding, moving radially outward from the nucleus. Each subsequent rotation, each 16.16-hour cycle, injects another pulse, another enhancement, creating a rhythmic pattern, a series of shells, density maxima separated by 16.16 hours times the expansion velocity, thousands of kilometers of separation in the inner coma. These structures are subtle, hard to detect, requiring careful image processing, but they're real, genuine manifestations of the rotational heartbeat propagating through the entire comet system. Even the tail structures respond, the anti-tail, that peculiar feature appearing to point toward the sun, caused by dust grains in the orbital plane catching light at specific angles, shows slight modulation with rotation, as does the main tail. The dust and gas streams swept back by radiation pressure and solar wind, brightness variations, subtle shifts in structure, tied to when and where material is released, which depends on rotation, on which active areas face sunward at any moment. So the tails preserve a memory, an echo of the rotational state hours or days earlier, when the material composing them was ejected. Color variations prove subtle, requiring precise photometry and multiple filters, simultaneously if possible, to eliminate brightness changes and isolate true color shifts, but they exist. Green emission from C2, from diatomic carbon, appears stronger from the more active hemispheres. This green emission, a characteristic cometry feature visible even in small telescopes, comes from carbon-bearing molecules photo-dissociated by sunlight, broken apart, with the fragments emitting green light before dissociating further. More active regions, outgassing more vigorously, produce more parent molecules, leading to more C2 and thus stronger green emission. This creates subtle color modulation, the comet appearing slightly greener when active regions face Earth, slightly less green when they rotate away. Dust release becomes episodic with rotational facing in a beautiful example of cause and effect. When an active region rotates into direct sunlight, into the afternoon of its local day when surface temperatures peak, gas production surges. The increased gas flux can entrain larger particles, drag more dust aloft, overcome gravitational binding more effectively, so dust production peaks, creates bright jets, creates enhancements in the coma brightness. Then as that region rotates into evening, into sunset, into the long cold night, gas production wanes, dust entrainment decreases, the jets fade, weaken, nearly disappear. This episodic behavior, pulsing with the 16.16 hour rhythm, creates the observed brightness variations, the heartbeat we detect across millions of kilometers. The slow rotation, this 16 times 16 hour patient cadence, preserves jet coherence over not just hours but days. A jet formed when a particular active region faces the sun might remain visible, identifiable, traceable in images for several rotations, for days of Earth time. This persistence allows detailed study, allows tracking of jet evolution, allows scientists to see how individual structures change, evolve, weaken or strengthen over timescales long compared to the rotation period. These would be impossible with rapid rotation, where jets would appear, sweep across the sky, and vanish within hours, and showed how rotation controlled every aspect of activity, just as we infer for 3 Atlas. The similarity in phased outgassing between solar system comets and this interstellar visitor proves fascinating. Here we have a body formed light years away, under potentially very different conditions, around a different star, perhaps in a protoplanetary disk with different composition, different temperature profile, different dynamics, yet its behavior, its rotational control of activity, its phased jets and brightness variations mirror what we see in solar system comets. This suggests universal principles, physics that operates identically regardless of stellar system, composition that converges to similar outcomes. Or perhaps just that comets, wherever they form, represent a common end state, a typical outcome of icy planetesimal formation. The interstellar origin doesn't create something alien, doesn't produce exotic behavior incompatible with our understanding. Instead, we find the familiar, the expected, rotational modulation, phased outgassing, double-peaked light curves, all the features we've learned to recognize from studying solar system comets appear here too, in this visitor from beyond. This familiarity allows confident interpretation, lets us apply decades of cometary science knowledge, transfer understanding from one population to another, bridge the gap between the local and the galactic. This spin state, this 16.16-hour rotation, likely reflects formation conditions in that distant protoplanetary disk. Perhaps the region where 3I Atlas formed was particularly quiescent, low turbulence, gentle collisions, allowing accretion to proceed slowly, building up mass without imparting high spin. Or perhaps the body formed in the outer disk, where material moved more slowly, where orbital velocities were low, where angular momentum per unit mass was reduced compared to the inner disk. These formation scenarios, these possibilities, can be tested, refined. As we discover more interstellar objects, as we build statistical understanding of their properties, their rotation rates, their compositions, their orbital characteristics, low excitation from gentle ejection makes physical sense. If a body is gravitationally scattered violently, passing very close to a giant planet, experiencing intense tidal forces, it might gain rotational energy, might be spun up by tidal torques, emerge into interstellar space rotating rapidly, chaotically. But if ejection is gentler, occurring over longer timescales, through gradual migration, through resonant interactions that slowly raise the orbit, then rotational state remains nearly unchanged, primordial spin preserved. This scenario fits 3I Atlas, fits the slow rotation, the stable period, the lack of tumbling or complex dynamics, and once in interstellar space, once liberated from planetary influence, once drifting between the stars, there's truly nothing to change the rotation. The interstellar medium, even in relatively dense molecular clouds, contains only hundreds or thousands of atoms per cubic centimeter. For a kilometer-sized nucleus, the collision rate with interstellar atoms is negligible, might add or remove 1 or 2 atoms per second from the surface, utterly insufficient to affect rotation. Cosmic rays, high-energy particles, penetrate the surface, cause chemical changes, but they carry negligible momentum, can't torque the nucleus, can't alter its spin. Starlight from the galaxy, diffuse radiation from all the stars combined, exerts radiation pressure, but again, too weak, too distributed, to create significant torques on a tumbling irregular body. Only if the nucleus had enormous reflective sails, had extreme shape asymmetry, might galactic starlight matter and the interstellar magnetic field, though it permeates the galaxy, couples only weakly to neutral matter, can't grip an uncharged icy nucleus and torque it, so the rotation from formation is preserved across the parsecs, across the ages. Billions of years of travel might be the reality. If 3I Atlas formed in a stellar system several hundred light-years distant, a plausible distance given galactic stellar densities, and if it travelled at typical ejection velocities of a few kilometers per second, then the journey might span hundreds of millions or even billions of years. During all that time, during all those billions of rotations, the period remained unchanged. 16.16 hours, 16.16 hours, 16.16 hours, a cosmic clock unwinding, but never varying its rate, never deviating from its ancient rhythm. This pulse rhythm truly becomes the heartbeat of an ancient body in the most literal sense, beating steadily, unchanging, since before Earth's continents formed their current shapes, since before the dinosaurs, since before complex life, perhaps since before the sun itself ignited. If 3I Atlas is truly that old, each rotation a heartbeat, each pulse a reminder of unimaginable age, of journeys beyond comprehension, of loneliness and isolation measured in light years and eons. All this data flows into databases, digital archives maintained by astronomical organizations, the Minor Planet Center, the Planetary Data System. Others, light curve databases, preserve not just the final period, not just summary statistics, but the actual photometric measurements, thousands of them, each time-stamped, each calibrated, each representing a single brightness measurement at a specific moment. Future researchers, perhaps decades from now, can retrieve this data, reanalyze it, apply new techniques, test new theories, extract information we haven't yet imagined seeking. Future observations will continue tracking long-term stability as long as the comet remains bright enough. As it recedes, moving outward from the sun, back toward the depths from which it came, it will fade, dimming month by month, eventually reaching a point where even the largest telescopes struggle to detect it, where photometry becomes impossible. But until then, observers will continue monitoring, watching for any period change, any evolution, any hint that the rotational state is not perfectly stable. Any period change, even a tiny one, would indicate mass loss asymmetry, would tell us that material is being removed preferentially from one region, creating unbalanced torques. This would reveal details of outgassing distribution, of which areas are most active, of how sublimation varies across the surface. The upper limit on period change, the stringent constraint that no variation exceeds 0.01 hours, therefore constrains outgassing distribution, tells us that activity must be relatively balanced, symmetric, distributed such that net torques remain small. Through rotational synthesis, the combination of observations from many viewing geometries, from many rotation phases, astronomers attempt nucleus mapping, creating maps of surface features, identifying active and inactive regions. This technique, developed for asteroids and refined for comets, uses brightness variations, changes in how the object looks from different angles, to infer surface properties. Where are the bright spots, the dark regions, the active areas? For 3i Atlas, estimates suggest active area fractions of 10 to 30%, meaning that only 1/10 to 1/3 of the surface actually produces significant outgassing. The rest remains dormant, covered in lag deposits perhaps, layers of non-volatile dust and organics left behind as ice's sublime. These lag deposits build up over time, insulating the ice beneath, preventing further sublimation until they crack, until jets break through, until fresh ice becomes exposed. This creates the patchy activity, the discrete jets, the focused structures we observe rather than uniform outgassing from the entire surface. The light curve, in its shape and amplitude, encodes information about the inertia tensor, a mathematical object describing how mass is distributed, how the body resists rotational acceleration about different axes. A perfectly spherical uniform body has a simple inertia tensor, equal values along all axes, but an elongated body, one with mass concentrated along the long axis, has a different inertia tensor, one that reflects that asymmetry. By fitting models to the light curve, by matching predicted brightness variations to observed ones, scientists constrain the inertia tensor, learn about internal mass distribution. This connects to fundamental questions of structure. Is the nucleus homogeneous, uniform throughout, or differentiated, with denser material perhaps concentrated toward the center, or layered, with composition varying from surface to core? The stable rotation, the unchanging period, the clean single-peaked or double-peaked light curves suggest relative homogeneity. No evidence for large-scale internal structure that would create complex rotational dynamics, precession, wobbles. Instead, we see simplicity, regularity, suggesting internal uniformity, or at least smooth gradients rather than sharp discontinuities. Slow rotators prove more common among larger nuclei. This is an observed trend in solar system comets. Smaller bodies, those just hundreds of meters or a few kilometers across, often spin rapidly, periods of a few hours, while larger bodies, those exceeding 5 or 10 kilometers, tend to rotate more slowly. The reason might be structural. Larger bodies have more mass, more self-gravity, can hold themselves together better. Smaller bodies, especially if loosely bound, can't survive rapid rotation. Centrifugal forces would overcome weak gravity, tear them apart, disperse them into rubble. So small bodies that rotate rapidly must be strong, coherent, while large bodies can afford slow rotation even if weakly bound. The size-rotation relation, this trend of larger bodies rotating more slowly, now extends to interstellar objects through 3 Atlas, with its estimated 4 to 8 kilometer diameter and 16.16 hour period. It fits the expected trend. falls where solar system comets of similar size would fall on a size rotation diagram. This suggests universality, suggests that the physics governing cometary rotation operates the same way, regardless of where a body formed, regardless of stellar system. The same forces, the same constraints, the same evolutionary pathways lead to similar outcomes. This is deeply reassuring. Tells us that our understanding, developed from solar system objects, can extend outward, can apply to the broader galaxy. For low-density bodies, those with bulk densities below 500 kilograms per cubic meter, less dense than water, porosity becomes essential. These are not solid blocks of ice, but sponge-like structures, networks of voids and passages, empty spaces accounting for perhaps half the volume or more. Such porous structures have weak tensile strength, can't withstand high centrifugal stress. Rapid rotation would pull them apart, disperse them into fragments. So slow rotation becomes necessary. 1616 hours provides gentle enough conditions that even a weak porous structure can survive, can maintain integrity, can hold together despite internal voids and fractures. This porous structure might arise from pristine accretion, from the original formation process. Imagine icy particles, each perhaps millimeters to centimeters across, drifting in the protoplanetary disk, colliding gently, sticking together through sintering, through ice welding where surfaces bond on contact, building up slowly, layer by layer, without ever compressing fully, without forcing out the voids. This creates a body that's mostly structural ice, with void spaces preserved, primordial porosity locked in since formation, never eliminated by subsequent processing. The rotational pulse reveals internal homogeneity through its purity, its simplicity. If there were large internal voids, if the interior were highly irregular, asymmetric, we might see complex rotational behavior, precession, nutation, wobbles superimposed on the main rotation, but we see none of this, just clean periodic variation, suggesting that while the body may be porous, it's uniformly porous, homogeneously structured, without large-scale asymmetries that would complicate the dynamics. No subnuclei have been detected, no smaller bodies orbiting within the coma, no companions to the main nucleus. Careful searches, examining images for point sources moving with the comet, looking for brightness variations that might indicate mutual events, occultations or eclipses between components, have found nothing. Just one nucleus, solitary, alone, spinning in isolation. This rules out certain formation scenarios, rules out recent tidal disruption that might split a body into multiple fragments, suggests instead that 3i Atlas has remained intact, single, coherent throughout its journey. No satellites either, no moons orbiting the nucleus, which makes sense given the small size. The Hill sphere, the region where a body's gravity dominates over the sun's, is tiny for kilometer-sized objects. Any satellite would need to orbit very close, within just a few kilometers, where tidal forces are strong, where stability is questionable, and the formation of such satellites seems unlikely, would require specific capture scenarios or formation mechanisms that probably didn't occur. This stable spin excludes recent disruption quite definitively. If the nucleus had suffered a collision, a splitting event, a catastrophic disruption within the last few orbital periods, we'd see evidence, complex rotation, tumbling, perhaps multiple components, but instead we see ancient stability, primordial calm, rotation that looks undisturbed, unchanged since formation. This tells us the interstellar journey was uneventful. No collisions, no close encounters with stars or planets that might have disrupted the structure. The pulse itself becomes a diagnostic of structural strength in elegant fashion. How much brightness variation can a body show before it must be solid? Before it must have significant tensile strength? The amplitude, the 0.3 to 0.5 magnitude variation, implies an axis ratio of 1.5 to 2.1, which requires some strength to maintain. A completely fluid body or a loose rubble pile might not maintain such elongation, might relax towards spherical symmetry. So the pulse tells us about material properties, about cohesion, about whether this is a coherent object or a loosely bound collection. This data informs models of extrasolar nucleus evolution in important ways. How do cometary bodies form in other stellar systems? Do they follow the same pathways as solar system comets? Do protoplanetary disks around other stars produce similar outcomes? Each interstellar object we study, each measurement we make, constrains these models, tests predictions, reveals whether planet formation is universal, or whether each system is unique, each rotation period measured, each composition determined, each trajectory calculated, adds to our understanding not just of comets, but of planetary systems in general. As Throat Atlas recedes from the Sun, as it moves back toward the interstellar depths, the rhythmic signal fades, not in period, not in regularity, but in detectability. The comet grows fainter, dimmer, more distant, requiring longer exposures, larger telescopes, more careful analysis to extract the signal from the noise. The brightness pulse continues. We know it continues. The nucleus still rotates, still turns its faces toward the distant sun. But our ability to measure it diminishes, fades, approaches the limit of feasibility. The final cycles were captured in late 2025. In November and December, pushing photometric capabilities to their limits. Observers used the largest available telescopes, integrated for hours, combined multiple nights of data, extracted every possible photon from the fading signal, and they succeeded. Measured rotation cycles even as the comet dropped below 20th magnitude, became fainter than all but the most patient observations could reach. These final measurements, these last rotations captured, complete the data set, provide the long baseline needed to constrain period stability over the entire apparition, before the comet becomes too faint for photometry, before it drops below the detection threshold, even for the largest telescopes. These final observations are archived, preserved, added to the permanent record. Future apparitions, if the comet's orbit ever brings it back, decades or centuries from now, will allow comparison, will reveal whether the period remained stable over the long gap, whether anything changed during the decades in the outer solar system or the centuries in interstellar space. Now let us drift deeper still into the implications, into what this heartbeat means, this ancient rhythm, this 16-16-hour pulse connects us to the deep past, to epochs before our world existed, to the era of stellar formation, of planetary birth, of cosmic dawn in some distant region of the galaxy. Every rotation we measure, every pulse we detect, echoes across those eons, brings news from unimaginable distances and times. The patience of this rotation, the slowness, invites our own slowing, our own patience. Feel your breath naturally sinking to the cosmic rhythm, not literally, not requiring 16 hours per breath, but symbolically, spiritually, letting go of urgency, releasing the need for speed, accepting the ancient cadence of the turning nucleus, the slow waltz through space, the measured revelation of hidden faces, ancient nucleus heartbeat. These words become a rhythm, a mantra, ancient nucleus heartbeat, pulsing steadily through the void, through the darkness, through the cold, never rushing, never hurrying, just being, existing, rotating with the patience of geological time, of astronomical time, of deep time measured in the turning of galaxies. Slow rotational whisper, another phrase to hold, to contemplate. The nucleus whispers through its rotation, tells its story through brightness variations, through the patient revealing of its shape, its activity, its nature. This is not a shout, not a dramatic announcement, but a whisper, quiet, subtle, requiring attention, requiring patience, requiring stillness to hear. 16-hour quiet cadence, the specific rhythm, the measured beat, 4 of our heartbeats per second, perhaps, compared to 1 rotation every 16 hours for the nucleus. Vastly different timescales, yet both rhythms, both pulses, both patterns of existence. We are fast, the comet is slow, yet both are valid, both are real. Both mark time in their own way. Feel yourself settling now, deeper into rest. The scientific details begin to fade, not forgotten, but receding, becoming less important than the sensation, the feeling, the pure experience of cosmic vastness, of ancient rhythms, of patient rotation continuing, unchanging, through space and time. Phased light serenity, the peace that comes from periodic variation, from knowing that the next pulse will come, will arrive, will happen as surely as the last one did. This reliability, this predictability, this cosmic clockwork brings serenity, brings calm, removes uncertainty, establishes rhythm, creates the foundation for rest, primordial spin peace, rotation that has continued since formation, since birth, unchanged by all the subsequent events, all the distance travelled, all the time elapsed. This is peace, this is stability, this is the calm of conservation laws, of physics proceeding inevitably, of ancient momentum preserved. Your breathing slows further now, deepens. Each exhalation releases more, lets go of more, surrenders more to the darkness, to the quiet, to the vast empty spaces between stars where Three-Eye Atlas drifted, alone, patient, turning slowly, waiting the eons until it would enter another stellar system, encounter warmth, brightness, activity, gentle pulse harmony, the harmony between rotation and outgassing, between spin and structure, between ancient formation and current observation, all in harmony, all aligned, all consistent. This harmony extends outward, touches you, invites you into its rhythm, into its peace, into its ancient cadence, turning rhythm calm, the calm that comes from measured rotation, from patient cycles, from rhythms that do not hurry, do not rush, simply turning, revealing, concealing, revealing again, the same faces, the same features, rotation after rotation, pulse after pulse, heartbeat after heartbeat. Feel the weight of your body, settling, sinking, supported completely. No need to hold tension, no need to maintain alertness, just rest, deep rest, cosmic rest, the rest of an ancient nucleus, rotating peacefully through the void, undisturbed, untroubled, simply being. Heartbeat revelation drift. Each pulse reveals something, then drifts, then reveals again. This is the nature of rotation, of periodic phenomena, revelation and concealment, brightness and dimness, ebb and flow, all drifting, all flowing, all part of the endless cycle, rotational cycle stillness. Even as the nucleus rotates, there is stillness, deep stillness. The rotation is steady, unchanging, predictable. This creates a deeper stillness, a calm within the motion, peace within the cycle, like your breath, which continues, yet within which you find stillness. Nucleus waltz surrender. The nucleus dances its slow waltz through space, 16 16 hours per turn, and you surrender to its rhythm. Let go into its patient cadence. Release into its ancient choreography. Surrender, release, let go. The darkness deepens. Silence grows. Words become less frequent, more sparse, space opening between them, vast empty space, cosmic space, the space through which Three-Eye Atlas travelled for millions of years, meeting nothing, encountering only void, darkness, cold, silence, absolute silence, broken only by its own slow turning, its patient rotation, its quiet heartbeat, phased awakening hush, activity that awakens, then hushes, then awakens again. Cycles of activity and quiet, of outgassing and stillness, following the rotation, following the patient rhythm, now hushing, growing quiet, fading toward silence. Spin's patient embrace, rotation that does not force, does not rush, but embraces, holds, maintains. patiently, endlessly. The spin embraces the nucleus, holds it together, provides structure, gives form. Patient embrace, loving embrace, eternal embrace. 16-16-hour breath. Imagine breathing that slowly. One inhale taking 8 hours, one exhale taking 8 hours. Impossibly slow. Yet this is the nucleus rhythm, its day and night, its cycle of illumination and shadow. Ancient, patient, slow breath. Longer pauses now, between phrases, between thoughts, space expanding, time stretching, silence becoming the primary texture, words just occasional markers, guideposts in the vast emptiness. Illumination dance integration, light and shadow dancing, integrating into wholeness. The bright hemisphere and the dark, the active face and the dormant, all parts of one whole, integrated, complete, dancing slowly together through space. Active face memory, the memory held in the light curve, the record of which faces are active when jets appear, where outgassing emerges, memory encoded in data, preserved, eternal, fading now, receding, becoming one with the void, coherent jet persistence, jets that persist, that maintain coherence, that continue, then fade, then return, persistence through cycles, through rotations, through time, now fading, weakening, as distance increases, as the comet recedes. Rotational balance void, balance maintained through rotation, equilibrium preserved, now releasing into void, into emptiness, into the vast spaces. Balance becoming stillness, equilibrium becoming peace, rotation becoming rest, primordial inertia flow, the original momentum, the ancient spin, flowing forward through time, unchanging, eternal, now flowing into silence, into darkness, into the deep rest that awaits, heartbeat cosmic solitude, the pulse, the rhythm, in absolute solitude, alone in the cosmos and between stars, no companion, no witness, just the patient beating, the steady rhythm continuing forever, fading now into silence, vast emptiness, endless darkness, infinite patience, ancient turning, quiet pulse, deep peace, eternal turn release. The turning continues, eternal, endless, but you release, let go, surrender into sleep, into rest, into the void. The nucleus turns, you rest, release, drift, interstellar wanderer serenity. 3i Atlas, the third visitor from beyond our solar system, drifting from distant stars, carrying secrets of other worlds, its serenity unbroken, even as jets pulse forth, vaporous tails trailing, one of dust, one of gas, twin veils in the cosmic wind, serenity in motion, serenity in the pulse, inviting you deeper into calm, jet symphony whisper, the outgassing jets, synchronized to the spin, whispering their symphony every 16 hours, ice sublimating, gases escaping, brightness surging, then waning, a whisper from the nucleus, core of ancient ice and rock, formed in the cradle of another sun, now whispering across the void to our telescopes, to our wandering minds. Hear the whisper, feel the symphony, let it lull you. Discovery echo fade, Echoes of its finding, July's gaze upon the sky, Atlas telescope capturing the faint glow. Now those echoes fade as the comet recedes, hyperbolic path carrying it away, never to return. 1.8 AU from Earth, a safe passage, no collision, just a fleeting visit, echoes softening, memories dissolving into the fade of night. Alien speculation hush, whispers of artificial origins, pulses too regular, too precise, yet nature's hand, rotation's gift. Hush the speculation, embrace the natural wonder, the interstellar messenger, not crafted, but born of cosmic forges. Hush now, let the mystery dissolve into acceptance, into peace. Tail duality balance, two tails, ion and dust, balancing the form, one blue, glowing with solar wind, one white, scattering light. Duality and harmony, push and pull, visibility and shadow, balance extending to your own duality. Wake and sleep, tension and release. Find balance in the tail's silent dance, velocity veil calm, jets escaping at hundreds of meters per second, yet the whole remains calm, unhurried. Velocity veiled in slowness, the 16.16 hour cycle overriding haste, calm prevailing, drawing you into its veil, where speed surrenders to rhythm. NASA gaze integration, eyes of Hubble, of Webb, capturing the pulses, the mysterious signals, integration of data, light curves plotted, rotations mapped. Now integrate into your being, the gaze of science, merging with intuition, with rest, all one, all harmonious. Hyperbolic path release, unbound trajectory, no orbit, just passage, release from gravity's hold, free in the galaxy. You too release from earthly binds, from daily spins, into hyperbolic freedom, drifting outward, unbound, pulsing light eternal, the light that pulses, eternal in its cycle, even as it dims, as perihelion passes, eternal reminder of cosmic constants, of rhythms beyond time, now eternal in your subconscious, pulsing softly as you sleep. Deep space invitation, invitation to join in the deep space journey, millions of years alone, now shared in this moment. Invitation accepted as eyelids grow heavy, as thoughts disperse into the invitation of slumber. Silent witness drift, 3 Atlas, silent witness to galaxies, to nebulae, now drifting past our sun. Witness no more, just drift. You drift with it, into silence, into the cosmic current. Final hush expansion, hush expanding, filling all, their words ceasing, yet only the hush, the expansion, into infinity. Hush, expand, sleep, silence, deep silence, cosmic silence, and in that silence, in that vast emptiness, in that ancient patient darkness, we find ourselves returning, drifting back as if on a cosmic current, as rotation brings us around once more. 16.16 hours completing, a cycle ending, a cycle beginning, seamlessly, endlessly,